is the first time, I guess, in 2 years that we've had a face-to-face seminar. For all the students, if you don't mind, before you leave, on the back table is a sign-in sheet. It's a way for me to also keep track of my 601 students, but then also if other students are getting extra credit in their classes. So it's back there, and please print your name. And Dr. Russell is going to introduce Jonathan.
Right.
Yeah. Well, I mean, I don't know.
It is.
That's
Good.
I saw it there. Okay.
Stick it in my eye.
Okay, I'll try not to.
Are we ready to go, or are we gonna wait a couple minutes, or wait till a couple after? It's 12.
I wouldn't wait beyond 5 after at the latest.
Let's wait till 2 or 3 after, just in case.
I've got right at 12. So while we're sitting here, everybody watch Wave 3 at noon tomorrow. Dr. Russell's going to be on TV.
Where'd you do this?
About the Maker Faire Saturday. Maker Faire is a free event. It's gonna be in the SAC. Y'all should all come. It's gonna be great. And then we have our social event tomorrow afternoon, right? Here in the bath. Our social events in this.
Oh, yes, it's here tomorrow evening at
5?
5.
In this
5 to
room.
6.
So
So the format's just going to be a few announcements from Dr. Elbaz, myself, if there's any from the grad programs, and UMES, and then we'll have some light appetizers kind of stuff. It's time to hang out and come meet everybody. You'll see this room a lot this semester.
lights on. Just give it another minute. Everybody's too quiet. So there's almost 100 booths at the Maker Faire this weekend. Almost, but not quite 100. It's going to be pretty amazing.
Yeah. I don't remember that many before when it was outside.
So our NASA experiment will be there as well. Experiment that puts a space on it. All right, let's go ahead and get started, I guess. So today we have with us Jonathan George. Jonathan got his bachelor's degree at the University of Tennessee at Chattanooga in 1993, and went out into the world and worked for a while. In 2007, he actually had gone through some issues and was the recipient of a new liver. And I think the process of being a liver transplant recipient kind of piqued his interest in bioengineering and that process and all the technology that goes into it. He moved to Louisville in 2014, started working for a researcher downtown, and enrolled in our PhD program in 2016. In 2020, I think he entered into candidacy, so he's been doing research in my lab on pediatric spinal cord injuries, specifically making what we call rocking rehab, which is a rocking chair that is instrumented. It's for kids that have spinal cord injury. And he's here to talk about that today. So Jonathan, welcome. Don't point me in the eye with that laser.
Thank you for that. Yeah, so I guess getting a liver transplant kind of, I guess it put some real meaning into all this technology, because, I mean, actually through that whole experience, there were several different times when I wouldn't have made it if it weren't for specific, or lots of pieces of technology that came together to enable that, and a lot of good doctors and things too. So, you know, it had always been a bit of an interest to me, but after that, and I was looking to sort of reboot my career after being on disability for a while, I took the opportunity to move over into bioengineering, and I've really been enjoying it so far. So today, I'm going to talk about some work we've been doing with the folks over at Fraser Rehab, looking at kids with spinal cord injuries and what we can do for them. So I wanted to kind of review some of the background of spinal cord injury in children. So when we think about spinal cord injuries, the first thing that comes to most people's mind is paralysis, you know, paralysis of arms and legs, and maybe the inability to walk. They often use wheelchairs. But really the effects of spinal cord injuries, especially in kids, is a whole lot more far-reaching than just paralysis of arms and legs. It affects pretty much every body system there is, including all those you see listed there. And in addition to the immediate effects on these body systems, there's longitudinal outcomes, and those are especially pronounced in kids with spinal cord injuries. So the fact that they're still growing leads to some impacts. And one of the things, I've got head and trunk control highlighted there partly because that is actually one of the things that is specifically for kids more impactful. And also because the project I'm working on specifically targets helping these kids with their head and trunk control. So when a kid gets a spinal cord injury, the fact that their skeletal system is still growing, their bones are still growing and maturing, leads to the risk for certain chronic conditions such as pneumonia and scoliosis. And actually those two are linked because, you know, as you grow, as your bones grow, they grow in response to stresses applied to them by muscles and by load bearing and things like that. And so if a kid can't run and play and jump and things like a kid normally would, but is instead sitting in a wheelchair all the time, and also in addition to that is cannot use their muscles in the way they normally would, their skeletal system develops wrong, and they'll get really bad scoliosis. Scoliosis is spinal curvature. It's defined as greater than 10%, but most of these kids will end up with really bad scoliosis. They often have to have surgery to correct it. The scoliosis can compromise respiratory function, which leads to pneumonia, and it also can lead to things like pelvic obliquity, so they're sitting crooked, which can lead to pressure sores, which can be a really serious complication for these kids also. So this is, it's not just sort of even just a quality of life thing, it's a serious issue that can compromise their health. So at Fraser Rehab, they've done actually some really groundbreaking research and development of what they call activity-based therapy. And this is a method of therapy that attempts to duplicate normal patterns of movement as closely as possible. The idea is that when you get a spinal cord injury, typically, you know, the instructions to the muscles, to activate muscles, comes from the brain and goes down the spinal cord, and then the spinal cord relays those instructions to the muscles. But what we've found is that the spinal cord actually can do more than just, it's not just a passive conduit for information. It can actually organize muscle activation on its own. And so after spinal cord injury, when we're no longer getting those signals coming down from the brain, we can retrain the spinal cord to listen to sensory input from below the level of the injury and train the spinal cord to activate muscles in ways that are appropriate. And that can help with many of these things that we listed earlier, many of these effects, and especially with trunk control. So activity-based therapy, locomotor training is sort of the core centerpiece of activity-based therapy. It's the primary therapeutic intervention. So what they do with these kids, they put them in a harness, kind of like a climbing harness that supports their body weight, and then they put them on a treadmill and have them walk. Now they can't walk on their own typically, so they have the therapist assist them to move their legs in an appropriate walking motion. And this helps them to reinforce the appropriate alignment of the trunk, pelvis, and lower extremities. It helps retrain their spinal cord to activate muscles, including the postural muscles that help with trunk control. And they've actually done research on this and done studies that show that these kids who participate in this gain significantly in trunk control. So these kids, when they go through this activity-based therapy, they regain a lot of function. But they don't want to send the kids home and have them sit in their wheelchair again and not use that capacity that they've regained. So they want to integrate this capacity that they've gained into their home life, their community life. But the challenge is finding ways they can do that, because they're typically still impaired. The activity-based therapy helps a lot, but it doesn't bring them all the way back to where a typically developing kid would be. So one of the things that they thought of that they could do, and this is specifically targeted at trunk control, is put the child in a rocking chair. So this is the first little girl that they put in a rocking chair, and they had her rock in the rocking chair, but there were problems. It wasn't really safe. That was just an off-the-shelf rocking chair that they'd modified. So they asked us, they came to us and asked us if we could design a rocking chair that would be safe for these kids. So we did. We designed a rocking chair like you see here with a nice stable base. It's a glider style rocking chair. It's been tested very thoroughly to make sure the kids couldn't tip this thing over if they, no matter how hard they rock the rocking chair, they can't tip it over. It's adjustable so it can fit different sizes of kids. But what I'm talking about today actually is some extra things we've gone on to do with this rocking chair. So we've added a bunch of sensors to this. Initially, it was like an accelerometer and a position sensor, and those allow us to just simply track how much time the kid is rocking in the rocking chair, the amplitude of rocking, just see how they're using it. But we wanted to go further than that and see if we could learn more about the kids while they're rocking, what muscles they're using and things. So we added a number of other sensors. We put sensors in the footrest. We put load cells in the footrest. This is configured essentially like your bathroom scales. It's four load cells connected in a Wheatstone bridge configuration. So as force is applied to the footrest, it changes the differential voltage on that Wheatstone bridge. We can read that with an amplifier and then send that data off to the MyRio 1900 that we're using to capture this data. We also put force sensing resistors in the seat. This is a TPU, 3D printed TPU pad that we made with recesses in there that we can put these force sensing resistors in. The force sensing resistors are variable resistors that as pressure is applied, the resistance goes down. We also 3D printed what I call, it's like an actuator plate that sits on top of the force sensitive resistors and increases the sensitivity of them to the forces that the child applies while they're rocking. That's set up as a voltage divider with each FSR is paired with a fixed value resistor. And then as the resistance of the FSR varies, the voltage varies, and we can read that. Similarly, we have FSRs on the armrests. Those are a different form factor. They're these long, narrow FSRs, again with an actuator plate over top, and these have a pad sitting on the armrest. And that setup allows it so that wherever force is applied to that armrest pad, we can read that as a signal. So we also wanted, that gives us some input at least from arms, legs, and the seat gives us some input from leg motion and some input from the trunk as the trunk moves. But we wanted something to better read the motion of the trunk. And we could have put force sensing resistors again in the back of the seat. But then as soon as the child leans forward and is no longer in contact with the back of the seat, we lose all information about what they're doing. So these kids, when they're in the rocking chair, they typically will have a belt around them to hold them in the seat and keep them safe. So we thought, well, maybe there's something we could do with that belt. Maybe we can look at the tension in that belt and read that. So we started looking into that, and there was another group. This research that I'm doing is being supported through the NSF EPSCoR grant that a lot of institutions in Kentucky, including U of L, are participating in. And one of the other groups, Dr. Harnett's lab here on campus, was developing these soft optical sensors. And those look like they'd be ideal for integration into this belt as a sensor. So these rely on a time of flight sensor that actually looks at the time for an emitted pulse of light to return back to the sensor, and can use that to read the distance that that light has traveled. These were designed, these low-cost ones that are available now were designed as for mobile phones. So when you take your phone and put it up to your face in a call and it turns the screen off, that's using typically a sensor similar to this, where it can tell that there's something close to the screen and won't let you accidentally push buttons with your face. So we're using one of these sensors from ST Microelectronics. It uses 940 nanometer wavelength, which is a good match. We're using stretchable fiber optics in this, and that wavelength works well with the fiber optics that we're using. But these were meant to transmit light in free space, not in a fiber optic waveguide. So we have designed fixtures to connect this sensor to stretchable fiber optics. So the stretchable optical fibers, they have a urethane core and silicone cladding, and those have been, so a loop of that fiber has been sandwiched between two pieces of elastic fabric and then heat bonded into that fabric. And then there's these tabs on either end, tabs here and here, that you can pull on that, and that stretches the optical fiber and changes the effective length of that optical fiber, which changes the time it takes for the light to travel through it. So we use a little mirror underneath or above, depending on your configuration, the emitter and detector to route the light into that fiber optic. So then we also designed a little mount, a 3D printed mount that connects to that fabric, and that has a clamp that will hold the fiber optics in place, and also provides a place for the time of flight sensor to be mounted over that angled mirror. You can see the clamp that we secure the fiber optics. There's the optical fibers, and there's the clamp, which we screw down, and then it's a little hard to tell what's going on, but this is actually the mirror, and these are the reflections of the fibers, and then here's the optical fibers. There's little channels that they run into this mount. We also designed a bracket to place that belt, so it wouldn't slide down. Designed that and 3D printed it. And that also is connected to our Rio, my Rio, and we capture the data via I2C. So while the kids were rocking, we could see that I could watch the data coming in and tell the data we were getting from that strap sensor was, responding to the movements of the child. And we could see that also in our data as we pulled it in. But we wanted to come up with a better model that we could actually use that sensor, that strap data, as well as all those other sensors to predict muscle activation. So we wouldn't have to use something like EMG to tell how the child's muscles were being activated. So we brought kids into the clinic. We brought in 10 kids with spinal cord injuries and 10 typically developing kids. And in order to get a sort of a ground truth that we could tell what the muscles were actually doing, we did hook up EMG. So we looked at 12 muscles on both sides of the body, so 24 total channels, muscles in the arms, the legs, and the trunk. And as you see, the EMG is on top here. That's just one channel. There were 23 others. And then this is actually the position data from the rocking chair position sensor, but we had 9 other sensors that we were recording the data for. So we brought in the kids. This is the demographics of the kids with spinal cord injuries. The ages ranged from 2 years old to almost 11 years old. The etiology of the different spinal cord injuries were quite varied. Some injuries during birth, some during performing a back bend, and then a number that were things like tumors on the spine, things like that. And a variety of times since injury and levels of injury. So a quite diverse group of kids. We brought these kids into the clinic. I don't know why this isn't playing this last time I presented, but so we brought them into the clinic and put them in the rocking chair, and we did 5 different, I call them rocking tasks. But the 2 most important were one that we called quiet sitting. So typically when you take EMG data, you try to, let's see. It says it's playing, but it's not. So when you take EMG data, you need to calibrate the EMG. So typically they'll ask the patient to give a maximum contraction of their muscle, so activate that muscle as hard as they can. But when you're working with someone with spinal cord injury, that doesn't really work because, of course, we're hoping to get some activation of even muscles with paralysis, but they can't voluntarily activate those muscles. So instead, we use a quiet sitting as a baseline to calibrate the EMG. So we have them sit quietly for about a minute, and then we'll run through the data and try to find, these kids fidget and it's hard to make sure they have quiet muscles the whole time. But we'll run through that data and find areas of the data where the muscles are at their lowest point of activation. Use that as our starting point, our calibration data. Then we have the kids, we just tell them to rock any way they want. We call that rock as you want. And they just rock any way they want for a while. And that is actually our primary data set that we use for most of our analyses, because we want to know how the kids will rock and what muscles they're activating. If we say gave them the rocking chair and sent them home with it, that's what we want to know. And then we have like 3 other rocking tasks where we tell them to rock using specific muscles or not using other muscles, just so we make sure that we have some data with those muscles activated. So like we'll tell them to try to rock using their legs, try to rock using their, shifting their weight with their trunk. We're doing, with this data, we're doing a number of different analyses. analyses. But the one I'm talking about right now is the machine learning to predict muscle activation. I feel a little bit hesitant to talk about machine learning because it's something that's kind of new to me, and we have some real machine learning experts here in the audience. So if anyone has any feedback, I would appreciate that as I go through this at the end. So we're in order to predict muscle activation, we have to define what we count as muscle activation anyway. And so in the literature, with people with spinal cord injuries, typically a 20% increase in EMG amplitude, RMS EMG amplitude over that quiet sitting amplitude is defined as muscle activation. So, but before we can do machine learning, we got to do some data processing. The EMG data that we captured was captured on the system over at Fraser Rehab at 2,000 hertz. My sensor data was captured on my laptop in a LabVIEW program that we wrote at 40 hertz, and that's different. You can't just mash the files together. So actually, over the summer, Grant Morgan was working with me, and he did a bunch of work in MATLAB on setting up some scripts that we're using to synchronize and combine this data. So we have, throughout these data files, both data files, we have manual pulse points where they push a button and it injects a signal into both data files, and we can use those to synchronize the data and then to interpolate the 40 hertz data up to 2,000 hertz. So once we've done that, we split the data out into separate data sets. For this analysis, we split out the quiet sitting data and the rock as you want data. I removed the offset in the EMG by subtracting the mean of the data for each muscle from each data point. We have a pretty constant DC offset in this EMG data, so this method works quite well to remove that offset. We then take a moving window RMS of the EMG data. We found that 300 points for a window size works well. And by taking that RMS, we do a couple things. We rectify the data, so we can take average amplitudes and things like that without just averaging out to zero. And it also helps to accentuate the areas of highest muscle activation. So then, to set up the data for machine learning, we have to find the relative amplitude of the EMG data in that rock as you want data. So we step through the quiet sitting data and find the lowest average amplitude for each muscle. In that case, we use 600 data point window, just to say, look at 600 data points, and then step through that data and find which 600 point window is the lowest activation. We then take that, we store that lowest activation value for each muscle, and we go through our rock as you want data and divide each data point by that same lowest average amplitude number. And that typically gives us activation numbers ranging anywhere from 1 to 3 is pretty typical. Occasionally we find a muscle that's actually activated less than the quiet sitting data was. And occasionally we find muscles that are activated up to 10 times as high as quiet sitting. So then I, similarly to what we did with the EMG data, we remove the offset from the sensor data by subtracting the mean. Some of this sensor data has, in addition to a DC offset, has a little bit of drift, so I may in future switch to a high-pass filter for that. But currently I've been subtracting the mean. Then I take the EMG data. I don't need to know what the muscle activation is 2,000 times a second. So I take it in 1 second chunks and calculate the relative amplitude, the mean relative amplitude for each 1 second chunk. And then I do the same thing for the sensor data, except instead of averaging out the whole second, I take the first half of the second and the second half of the second, calculate the mean RMS amplitude for the first and second half of each second. And that gives me some time-dependent information about this data. So right now, I'm right in the middle of this work. I haven't even completely processed all my data sets for training. But right now I've got 6 data sets processed, and I have those combined into a data table for training the machine learning algorithms. I'm using MATLAB regression learner for my machine learning. My predictors are the sensor data that I just talked about from the previous 1 second, and my response is the activation of the selected muscle. So I've got 24 muscles to choose from, and I have to train the model for each muscle. I combined those data sets for training. Right now I'm working with the typically developing children. Working with the typically developing kids is an easier problem because they're more consistent in their rocking. The kids with spinal cord injury have a wider variety of methods for rocking. So it's going to be interesting once I get into that to see how well this will work. I tested 19 different learning algorithms. They're the ones that are built into MATLAB. And baked trees consistently perform best. I need to do more testing, and I actually am looking into other algorithms that take the time series nature of this data into consideration. But this is what I've got right now. So I trained the model, and I tested it on 1 data set. And of course working on training more, on adding more data sets to that training data. This is the first, I picked out 3 muscles just to sort of in detail show what the training and validation of these models looked like. So you can kind of see here, we've got 4 data sets, 1, 2, 3, 4. This was before I had the 6. And the blue is the actual data, and the yellow is the predictions. And so this is predicting in 1 second chunks. And to me, that looks pretty good. It's not following the shape of the curve there, but so what we're trying to get at is something that we can tell the therapist, this kid is using his trunk muscles to rock the rocking chair, and he's activating them at, roughly this level. We don't need to know second by second exactly what the activation is. We just need to know through this course of rocking, they were activating these muscles and not activating those other ones. So of course this is the training data, and you'd expect it to be pretty good. So then to validate that, we tested it on an independent data set that hadn't been trained on. And again, so we're getting the blue again is the actual, and the orangey color here is the predicted. And we're getting actual sort of between 120 and 130%. So that is activated, because anything over 120 is activated. And our predicted is about 170. So not perfect, but it would be telling the therapist that it's activated, the muscles are activated correctly, telling the therapist that the muscles are, I consider both of those would be sort of in a low to moderate level of activation. So this is another muscle. This is the oblique, right oblique muscle. Again, the training data looks pretty similar. We've got training data that goes from about 1. If you look at the y-axis here, it goes from about 1 up to over 3. So having a good range of values in the training data is important, because if you don't have a value in the training data, it won't know what that looks like in the sensor data. So that actually tested out pretty good too. We got a prediction of 200%, and our actual range between 200 and 300%. So then I threw a really tough one at it, and this is tough because these numbers are, multiply these by 100% to get the percentage. So we're between about 3 and 8, so really highly activated in all of our test data sets, our training data sets. But in our validation data set, it was actually below 100%. And so since there wasn't anything that looked like this in the training data, it overshot it by a lot. Now the other thing that's possibly going on here is, if you looked at this training data, this is the this was the left tibialis anterior. And of course that's a leg muscle, and my sensors, if you saw back when I was talking about the footrest, the sensors in the footrest measure both legs together, right? So if it uses that footrest sensor data to try to predict this, it doesn't know which foot you're pushing with. And this kid actually was using their tibialis anterior on their right leg quite a bit. It was highly activated. So that may be what we're picking up here, and we may need to pool that data from the left and the right in order to get better results here. Final muscle, this I just threw in for interest. I wanted to see how well I could predict, how good of a model I could create just using the strap data. So that strap with the soft optical sensor. This is the cervical paraspinal muscle, which of course is up here, sort of in the back of the, lose your head like this. So I wanted to see how much information we were getting about that specific muscle based on the strap. So I trained a model just using the data from the strap, and you can see this is a little more scattered than the first model, which is also the cervical paraspinal muscles. But the actual prediction is actually a little better than the one from all the data. So that was interesting. I'm not sure what conclusion to draw from that, but it was interesting. So my final thing that I did, this is actually based on a little bit larger training data set, and I ran through all the muscles and then tested with another data set. So here you see on the y-axis here, you've got the different muscles, so cervical, paraspinal, and as you go down this, it's kind of going from the top of the body to the bottom. So these first 4 are trunk muscles, then we've got actually a trunk muscle down here. These are arm muscles, and then a couple trunk muscles here, and then leg muscles down here. So again, the yellow is predicted, the blue is actual, and then that blue area here is anything that doesn't come up to that line is not considered activated. So we had a couple muscles. If you look at right here, the blue here, in actuality they weren't activated, but our model is predicting low-level activation. Overall, we do track relatively well on our predictions and our actual, but again, this is preliminary data, and we need to do more training and possibly find some better models that take account of the time dependency of our data. So future work, I need to optimize the data further. I'd like to go through my sensor data and high-pass filter it instead of doing that mean to remove the offset. I want to explore some other learning algorithms that are designed for time series data, and I need to prepare the rest of my data sets for additional training and validation of models. So, but the preliminary results from the machine learning look promising to me. Again, we need to add more training data and do additional testing to validate the algorithms. I want to thank some people. This is my dissertation committee. Dr. Ursel, who introduced me, is my advisor, and Dr. Behrman works over at Fraser with all these kids with spinal cord injuries, and then the rest of my committee, the Bertaccis and Dr. Casada, have all been helpful. I also want to thank Dr. Popa, who has been with the EPSCoR, NSF EPSCoR project, who's been funding this work for the last few years. Dr. Harnett and Dr. Lin, who worked on developing and helping me with that strap sensor. I want to help thank Molly King and all the other folks working at Fraser who helped with all that data collection, with bringing those kids with spinal cord injuries into the clinic to collect data. And I also want to thank Grant Morgan, who worked with me this summer and did a lot of good work in MATLAB and helping me to collect this data. So with that, I'll ask if there's any questions.
So I'll lead off with a question that's kind of leading. So what's the importance of the machine learning part, and as related to the sensors that are on the chair and the fact that you have EKG or EMG, right? Why is the machine learning, why is that a great addition?
So, you know, actually when I wrote my proposal, we were going to I proposed that we just use traditional statistical regression methods to try to suss out what muscles were being activated based on the sensor data. But it kind of became clear to me that probably machine learning would do a better job and give us better information. And ultimately, what we want is information that will be helpful to the therapists. And by using those sensors, these are inexpensive sensors that we can put on the rocking chair. We can send the rocking chair home even and capture this data and then analyze it and tell the therapists what muscles, if we can tell them what muscles the child is using, tell them what's going on with their trunk control, things like that, based on the sensor data without having to, you know, use a $30,000 EMG system.
Yeah, that's the point I was trying to make.
Yeah.
Is that EMG is inconvenient and expensive.
Yeah, and you can't go and send it home with the kids. You got to bring them into the clinic. Yeah.
Follow up, what sort of accuracy do you think you need to be beneficial to these therapists? Like,
So I don't think we have to be extremely precise in telling them, okay, their muscle activation is 157% of quiet sitting. So I think if we can get low, medium, and high, you know, that will be great. But we do need to be relatively accurate as far as saying yes or no, is this muscle activated or not? And we don't have to be super precise in time. We can say, okay, over the last 5 minutes, they've been highly activating these muscles, moderately on these, and none on those. You know, that's the basic level of accuracy that I think we need. That's based on, you know, talking with the therapists. Yeah.
So, are you just collecting data from one visit, or are you collecting data from subsequent visits so you can see a trend?
Yeah, so right now we've done, the data that we're using is all from a single visit from kids. There are a few kids we brought in more than once, but that was typically just because they were in again and we went ahead and collected some data, or there was a couple cases where the EMG data had problems and we needed to recollect. So yeah, right now we're not doing we're not looking at change over time We're trying to do sort of more proof of concept. So the other thing we're doing with the ZMG data is we're doing a lot of work on sort of defining what muscles the kids typically use, what muscle activation patterns are typical in kids with spinal cord injury while rocking in a rocking chair. We're looking at things like, you know, where in the rocking cycle are different muscles typically activated. Sort of like in walking, you know what muscles typically are activated in like the legs during each phase of walking. And we want to do something, I don't think we can do something quite as defined in rocking because there's lots of different ways these kids choose to rock. You can activate all sorts of different muscles to make the chair rock. But we'd like to look at that and see if there's some typical ways that happens.
I'll follow up at the, I guess the dissertation proposal fell just short of saying we want the chair to track improvements in trunk control. Certainly that's what we think it could do. They don't really have a good mechanism now for knowing if the kids are getting better without always hooking them up to EMG and that kind of thing. So we saw the chair, number one, we wanted to make it safe. Number two, we said, hey, let's put sensors all over it because if we can tell that the kids are starting to use their legs after doing therapy, then you know you can, at first they're not, and then over time you'll see that they will, and so it's a way to track progress, as well as, you know, sending them home and being able, instead of sitting in a wheelchair, they're sitting in a rocking chair and doing this activity, which is feeding back to their